Okay, I'm now going to talk about isolated singularities. So if you have a function f of z and f is undefined at some point, call it z naught, we call z naught a singularity. And if there are no other singularities nearby, so there's some neighborhood around z naught where there are no other singularities, in that case, we call z naught an isolated singularity. So that's the meaning of isolated singularity, and isolated singularities, there are three types. So uh, the three types are as follows. You could have a removable isolated singularity. The second type is a pole. So, and the third type is what we call essential. And these are the three types of isolated singularities. Now, what do these three terms mean? Well, if you remember before when I was introducing the idea of a Laurent series, I talked about the principal part of a Laurent series. And I mentioned that it's important to be able to figure out how many terms make up that principal part. And the reason I said that is because that's what determines what sort of an isolated singularity you have. So, if you count, uh, if you count the number of terms making up the principal part of the Laurent series, so let's say you find a Laurent series that z equals z naught, so you'll get something like this, Cn z minus z naught to the power of n. And then you have a look and see what's the principal part, meaning what's the part where you have negative powers of z minus z naught. And you count how many terms there are in that principal part. If you have 0 terms which appear in the principal part, then z naught is called a removable isolated singularity. So it's removable if there are 0 terms in the principal part. So if you find a Laurent series and there are no negative powers of z minus z naught, you know it's a removable one. What about a pole? If there are m terms in the principal part, then that singularity is called a pole. And in fact, it's called a pole of order m. So if there are m terms, it's a pole of order m. If there's one term, that's still a pole as well, but usually instead of calling it a pole of order 1, we just call it a simple pole. And in fact, if it's a pole of order 2, we call it a double pole. Pole of order 3, we call it a triple pole. But after that, we start calling it a pole of order whatever the number is. And the final case, if in fact you have infinite number of terms in the principal part, so before I was assuming m was a finite number, but if it's infinite, then it's an essential singularity. So this is when you have infinite terms in the principal part. So you can use this definition and your knowledge of being able to compute the principal part to classify what sort of a singularity your function has. So let me show you some examples. Okay, so I'm going to classify the isolated singularity. So I'm going to take a bunch of functions that have a singularity at z equals 0. I'm going to classify what sort of a singularity that is in each case. So classify it as the isolated singularity z equals 0 for each of the following functions. Alright, so for A, I'll take the function to be sine z on z to the power of 5. In B, I'll take the function to be e to the power of 1 on z. For C, I'll take the function to be cos z minus 1 on z. And in D, I'll take the function to be z cubed cos z over e to the z minus 1 to the power of 7. Okay, so as you can see, each one of these functions has a singularity at z equals 0, because they're all undefined when z equals 0. But I want to classify what sort of a singularity 0 is in each case. So let's have a look at part A. Now, if I find the Taylor series for sine z, so remember, you should memorize certain Taylor series, like the exponential, sine, cos, and definitely 1 over 1 minus z. Those you should remember. So sine z, for instance, we know this is the sum from n equals 0 to infinity of negative 1 to the n on 2n plus 1 factorial z to the power of 2n plus 1. And if I write out the first few terms, so this is z minus z cubed on 3 factorial plus z5 on 5 factorial minus z to the 7 on 7 factorial plus z to the 9 on 9 factorial, etc., etc. So, right? And this is true for all z. This converges for all z. So now, assuming that z does not equal 0, I can divide through by z to the power of 5. If I do that, I get 1 on z to the 4 minus 1 on 3 factorial times 1 on z squared plus 1 on 5 factorial minus z squared on 7 factorial plus z to the 4 on 9 factorial, etc., etc. So you can see there are only two terms which involve a negative power of z. So there are only two terms in the principal part. Right? Because what I've written is the Laurent series for sine z on z to the 5 about z equals 0. And I can see that Laurent series only has two terms which involve negative powers of z. So what that means, it just means that z equals 0 is a pole of order 2. So that's how you can classify that one. Let's have a look at part B. Again, we know the Taylor series for e to the z. Right? We know that e to the z equals sum from n equals 0 to infinity of z to the n on n factorial, which equals 1 plus z squared on 2 factorial plus z cubed on 3 factorial plus etc., etc. And it goes on forever, and this, by the way, converges for all z as well. So now, if I replace z with 1 over z, what do I get? I get the Laurent series about z equals 0 which is now as follows. Times 1 on z squared plus 1 on 3 factorial times 1 on z cubed, etc. As you can see, because this is going to go on forever, this is going to have infinite terms that have a negative power of z. So there are infinite terms in the principal part. Right? So this is not, you wouldn't say this is a, instead of saying this is a pole of order infinity, like I said, the correct thing to say is that this is an essential singularity. So in this case, z equals 0 is an essential singularity. Alright, let's have a look at the next example. So part C, cos z minus 1 on z. Okay, so again, I'm going to use the fact, I'm going to manipulate the Taylor series for cos z. I know that cos z has Taylor series expansion going from n equals 0 to infinity of negative 1 to the n on 2 to the n factorial z to the power of 2n. And if I write out the first few terms of this is 1 minus z squared on 2 factorial plus z to the 4 on 4 factorial minus z to the 6 on 6 factorial, etc., etc. It just alternates like that forever. Now if we subtract 1 from here, as you can see, that first one is going to go away. So I'm left with this. Again, this is going to go on forever. And now, because I'm finding the Laurent series at 0, it's going to be in an annulus surrounding 0, so 0 is not included. I can divide by 0 here on both sides to get the Laurent series at 0. And this one is going to become minus z on 2 factorial plus z cubed on 4 factorial minus z to the 5 on 6 factorial, etc., etc. And now, as you can see, I don't have any negative powers of z in my Laurent series. So in other words, there are no terms in the principal part. So that means we call z equals 0 a removable singularity in this case. That's that one. Okay, let's look at the final one. So D, this one's a bit trickier. I want to classify singularities of cos z, z cubed cos z on e to the z minus 1 to the power of 7. Okay, so z equals 0 is not the only singularity here, right? Because e to the z equals 1 has quite a few solutions, infinite solutions. But definitely z equals 0 is one solution of that, and so z equals 0 is one of the singularities. Now how can I want to sort of see how many terms I have in the principal part here. Again, I'm going to manipulate Taylor series for cos and the exponential. So this can be written as z cubed, and I'm going to write the Taylor series for cos. 1 minus z squared on 2 factorial plus z to the 4 on 4 factorial minus z to the 6 on 6 factorial plus z to the 8 on 8 factorial, etc., etc. And on the bottom, what do we have? We know that e to the z is 1 plus z squared on 2 factorial, z cubed on 3 factorial, etc., etc. So if I subtract 1, I'm just going to be left with this. So ordinarily there's a plus 1 at the start of this series, but because we're doing e to the z minus 1, that's going to go away. It's going to be all this raised to the power of 7. Okay, so what you can do, you can take out a z cubed on top, and you can take, on the denominator, you can take out a factor of z from that bracket, and because it's raised to the power of 7, in actuality, you'll be taking out a factor of z to the 7 on the denominator. What you're going to be left with on the top is this one. And what you're going to be left with on the denominator is going to be this one. Plus z cubed on 4 factorial. Yeah. So, and this is what I'm going to call this guy g of z. So now this guy can be written as 1 over z to the power of 4 g of z. Now, what do you notice about g? Can you see that g is actually entire? It's analytic everywhere. Because if you have a look at that denominator, well actually, maybe I shouldn't say it's analytic everywhere, but it's going to be analytic at 0. When I put z equals 0 on the denominator, I'm not going to get 0. So it's going to be analytic in some neighborhood of 0, and so therefore I can find a Taylor series for it. So let me write some of this down. Note G is analytic at z equals 0, and you can, it's fairly simple to argue it's going to be analytic in some neighborhood of z equals 0. So therefore you can apply Taylor's theorem, which then tells you that g of z has expansion sum from n equals 0 to infinity of nth derivative at 0 over n factorial z to the n. Right? So we don't actually need to figure out what those coefficients are, because we're not actually concerned with what the principal part is. I just want to know how many terms there are in the principal part. So I'm just going to call the coefficients a0, a1z plus a2z squared, etc., etc. a5z5, that goes on forever. So then when z does not equal 0, I can divide both sides by z to the power of 4. And if I divide g of z by z to the power of 4, I just get f of z. Right? So this is going to become plus a4 plus a5 z to the 5, going on forever. So this is the Laurent series for the function f. I guess that was pretty bad of me. I should have labeled this and called this f of z, right? Anyway, this is the Laurent series for f of z at z equals 0. And as you can see, there are 4 terms that have a negative power of z. So there are 4 terms in the principal part. Therefore, z equals 0 is a pole of order 4. And that's how you would classify a singularity in that case. Okay, but there are other ways, and often the ways I'm about to show you are often quicker, that you can use in classifying the type of isolate singularity, because sometimes finding the Laurent series can be difficult, and so I'll show you these shortcuts. So I'll write the two results here. So suppose you have a function f and it has an isolated singularity at the point z equals z naught. Then the following are equivalent. Okay. So if I say z naught is a removable singularity, then that's actually equivalent to saying that it's possible to make f continuous at z naught. What I mean is that we can define f of z naught in such a way such that f becomes continuous at z equals z naught. And that's where the name removable comes from anyway. So you have a discontinuity at z naught, but if you can define f of z naught in such a way that removes this discontinuity, you get a removable singularity, right? So that's one equivalent definition. And a second equivalent definition for removable is that limit as z approaches z naught of z minus z naught of f of z is equal to 0. So if you have a function f and you have a singularity at z naught and you evaluate that limit and you get 0, that means that singularity is removable. So these are two, I guess, sometimes they can be shortcuts, not always, but these are two equivalent facts that are often quicker ways of checking if something's removable. And there are other equivalent definitions for removable as well, which I've left out here. You can see those in your lecture notes if you like. But these are the two main ones, which are practically used quite often. What about poles? So we also have shortcuts for poles as well. So the following are equivalent. So suppose z naught is a pole of order m. An equivalent definition of that is that limit as z approaches z naught of the modulus of f of z equals infinity. So if you take the modulus of f and take the limit as you approach a singularity and you get that limit equals infinity, then you would say that's a... Actually, you don't know what order it is, but you definitely know it's a pole. The second definition will tell you what order it is though. So an equivalent definition is we can write f of z equals g of z on z minus z naught to the power of m for some function g that is analytic near z naught and g of z naught does not equal 0. That's probably the one, I think, from personal experience. I think that second definition is the one I use most to see if something's a pole or not. So if you take your function f, and you can write that as g over z minus z naught to the power of m, and if g is analytic in some neighborhood of z naught, and g of z naught is not equal to 0, then that means Z0 is a pole of order m. Now, we don't really have, as far as I'm aware, we don't really have any shortcuts or equivalent definitions for essential singularities. Basically, if you have a singularity and you show that it's not removable and that it's not a pole, then by default it's just essential. That's the way it works. So there's no real shortcuts for that one. Okay, so let's have a look at some. So actually, before I move on, I'm going to do a fair few examples of this. You may want to jot down these shortcuts down. Pause the video and jot down these shortcuts because I'm going to refer to them a lot in the following examples. But anyway, the first example I'll do, let's have a look. I'm going to classify the singularities of, I'll take f to be cos z on z over z minus 1 to the 4. Okay, so just by looking at it, I can see I have singularities at 0 and 1, right? Because the denominator can't be 0. So that means z can't be 0 and z can't be 1. So singularities at z equals 0 and 1. So first let's think about z equals 0. So note we can write f of z equals g of z on z to the minus 1, z minus 1, oh actually, wrong way around guys, sorry about that. I should write f of z equals g of z on z, where g of z equals cos z on z minus 1 to the 4. That's what I should do. Alright, so that's easy to see. If you take g, as I've written it there, and you divide it by z, you'll get exactly f. Now, what do you notice about g? It's analytic near z equals 0, right? The only place where it's not analytic is z equals 1, so I can find some neighborhood near 0 where g is analytic. And also, can you see that g of 0 does not equal 0? Right, it's going to be cos 0 on 1, and cos 0 is 1, so it's not 0. So therefore, according to the equivalent definition I had for a pole, so therefore according to this fact here, I can see that z equals 0 is a pole of order 1, or a simple pole. Right? So that's all you need to do. And in fact, I'm going to use the same trick to classify z equals 1. So note we can write f of z equals g of z on z minus 1 to the 4. But this time I'm going to take g to be cos z on z. Okay. Now notice that when I define g in this way, this is still analytic near z equals 1, because the only place it's not analytic is z equals 0, and g of 1 does not equal 0, right? Because cos of 1 does not equal 0. So again, by that same definition, I conclude that z equals 1 is a pole of order 4. So that's basically it. So that's, as I said, that definition, that's probably the one I use most when I come to classify a singularity as a pole. So you just find some function g that's analytic near your point and non-zero at your point, and automatically know it's a pole. Okay, let's have a look at another example. Right, so now I'm going to classify the singularities. I'm going to take my function to be e to the power of z minus 2 minus 1 on z minus 1 and times z minus 2. Okay, so what about this one? So again, first of all, where are my singularities? Well, the only place where f is going to be undefined is when the denominator is 0. And that's precisely when z equals 1 and z equals 2. So singularities are at z equals 1, z equals 2. So they're isolated singularities. They're both sort of by themselves. They don't have anything immediately near them. So first let's have a look at z equals 1 to classify what sort of a singularity it is. Well, again, note we can write f of z equals g of z on z minus 1, where g of z, you would have to define it to be like this. Oops, that was supposed to be a minus. Okay, so that's g of z in this case. As you can see, g of z is analytic near z equals 1, right? Because the only place it's not analytic is when z equals 2. And g of 1 is non-zero. Because if you sub in 1 on the numerator, you're going to get e to the power of negative 1 minus 1, which is non-zero. So again, by that same definition that we had before, I can see that z equals 1 is a simple pole. Okay, now you may be thinking that you may have noticed a sort of pattern if I take a look back at cos z on z times z minus 1 on 4. It just looks like if you take your denominator and you see how many times a factor appears, that gives you a pole of order whatever. So for example, I have z minus 1 to the power of 4, because 1 is a factor of the denominator 4 times, therefore I have a pole of order 4. Or because z equals 0 was a factor of order 1 on the denominator, z equals 0 was a simple pole. And in this case here, I noticed the same thing. Z equals 1 was a factor of order 1 on the denominator, so therefore it's a simple pole. And you may think the same thing is true about z equals 2. But you have to be very careful, because usually that observation is true, as in usually you look at the denominator and you ask yourself how many times does the singularity appear as a factor, and usually that gives you a pole of order whatever, but that's only if the numerator is non-zero at your point. So for example here, in the case of z equals 2, if I try to apply the same trick from before and write f of z equals g of z on z minus 2, I would need to take g to be e to the z minus 2 minus 1 on z minus 1, right? But now, although this is analytic near z equals 2, although that's true, note that g of 2 is equal to 0. And that's the problem. If I sub in g equals 2 on the numerator, I get e to the power of 0, which is 1, and 1 minus 1 is 0. So g is 0 at my singularity, but remember from the definition, g should be non-zero at the singularity. So therefore, in this case, z equals 2 is not a pole, okay? So it's either going to be removable or essential. Now, let's check if it's removable. So to check if it's removable, I calculate the following limit. Yeah, and if this limit equals 0, I'll know it's removable. So let's see. This becomes limit as z approaches 2 of e to the z minus 2 minus 1. And I'm just going to get z minus 1, because the z minus 2 on the denominator is going to cancel. Sub in z equals 2 into here. You get e to the 0 minus 1 on 1, which is 0. So therefore, z equals 2 is a removable singularity. Right? So you just have to be careful when you come to identifying poles. You have to check that your numerator is non-zero at your point of interest.